Every power plant you've ever seen, every nuclear reactor, every coal station, every ship in the US Navy, they all run on the same basic idea. Boil water, make steam, spin a turbine. We've been doing this for 166 years, and we just got replaced. In December 2024, China switched on a machine that doesn't use steam at all. It uses carbon dioxide, pressurized to 200 atmospheres, heated to 700 degrees Celsius, and compressed into a state of matter that most people don't even know exists. It's called a supercritical CO2 turbine. It's 1/10 the size of a steam turbine. It's potentially 50% more efficient. And while America has been trying and failing to build one for over a decade, China just plugged theirs into the grid. So here's the question no one's really asking. Did the United States just lose the most important energy race of the 21st century? To understand why this matters, you need to understand a state of matter they probably didn't teach you in school. You know solids, liquids, and gases, but there's a fourth state hiding in your phase diagram. If you take any fluid and push it past a specific temperature and pressure, called the critical point, something strange happens. The boundary between liquid and gas doesn't just blur, it disappears entirely. What you get is a supercritical fluid. It has the density of a liquid, meaning it's heavy, and packs enormous mass into a small volume. But it flows like a gas, meaning it moves fast and fills every corner of whatever container it's in. Now here's where CO2 gets interesting. Water's critical point is at 374 degrees Celsius and 22 megapascals. That's extreme. But CO2 hits its critical point at just 31 degrees Celsius and 7.3 megapascals. That's barely above room temperature. And here's the thing most people miss. When water goes supercritical, it becomes a monster. Its dielectric constant crashes from 80 down to below 10. It stops behaving like the water you know. It starts dissolving the metal walls of its own pipes. Protective oxide layers that keep steel alive, supercritical water eats them. CO2 doesn't do any of that. It's chemically lazy. No ionic conductivity, no electrochemical corrosion. It just sits there, dense and cooperative, waiting to do work. That's why engineers have been obsessed with this molecule for decades. Every supercritical CO2 system runs on something called a closed Brayton cycle, and the version that actually works in practice, which most media coverage completely ignores, is called the recompression Brayton cycle. Let me walk you through it. You start with CO2 sitting at around 30 degrees Celsius, just below its critical point. It's already dense, 600 to 800 kilograms per cubic meter. That's the density of some light oils. It enters the main compressor, which pushes it up to about 20 megapascals, roughly 200 atmospheres. And here's the first enormous advantage. Because the CO2 is already so dense, the compressor barely has to work. Compressor work in this cycle is less than 1/3 of what a conventional gas turbine requires. Now, in the recompression variant, the flow actually splits. About 60% goes through the main recuperator, absorbing waste heat from the turbine exhaust. The remaining 40% gets rerouted through a secondary recompressor, bypassing part of the heat exchange. This split is critical. It eliminates what engineers call the pinch point problem, where temperature differences in the heat exchanger get so small that heat transfer effectively stalls. After recuperation, the CO2 might already be at 300 degrees before it even reaches the primary heat source. The main heater, whether that's nuclear, solar, natural gas, or waste heat, pushes it above 700 degrees Celsius. Then it hits the turbine. As it expands from 20 megapascals down to about 10 megapascals, it transfers its momentum into turbine blades, spinning at tens of thousands of RPM. And because CO2 is 100 to 1,000 times denser than steam at comparable points in the cycle, the volumetric flow rate needed for the same power output is dramatically lower. The result? A turbine that can fit on a conference table, producing the same power as a steam turbine that fills a warehouse. Theoretical thermal efficiency, 45 to 50%. Compare that to conventional steam at around 35%. In December 2024, the China National Nuclear Corporation announced that their system, called Chiton-1, was live and feeding power to the grid. Two 15-megawatt units bolted onto a steel factory's waste heat exhaust in Jiangsu province. The claimed numbers are stunning. 85% improvement in energy generation efficiency over the old steam system. 50% more net power from the same heat source. The entire system occupying 50% less space. Annual output, 70 million kilowatt hours, translating to roughly $4.3 million in extra revenue for the steelworks. Now, let's be honest about what this is and what it isn't. This isn't attached to a nuclear reactor. It isn't the primary power generation system for anything. It's waste heat recovery, essentially harvesting energy that was previously just dumped into the atmosphere. And that placement tells you everything about where the technology actually stands. If supercritical CO2 were fully mature, you'd see it integrated into China's HTRPM, high-temperature nuclear reactor, or powering a dedicated generation facility. The fact that it's on waste heat means the confidence level is good enough to deploy where failure is expensive, but not catastrophic. But here's what matters. They actually built it. They actually connected it. It's actually running. Meanwhile, the U.S. Department of Energy has been funding its own supercritical CO2 program, the STEP project, Supercritical Transformational Electric Power, based in San Antonio, Texas. It was supposed to be a 10-megawatt electric demonstration, the largest SCO2 test loop in the Western world. It has been repeatedly delayed. Turbomachinery problems, seal failures, bearing issues. As of now, it still hasn't achieved full power operation. And these aren't trivial engineering problems. Let me show you the three things that make this technology brutally difficult. First, materials. Above 550 degrees, conventional steels begin to creep, slowly deforming under load. And CO2 at these conditions attacks metal through a process called carburization. Carbon atoms diffuse into grain boundaries and form brittle carbides that crack over time. We have nickel superalloys like Inconel 718 that can resist this, but they cost tens of times more than structural steel, and we don't have 20-year reliability data. Second, the recuperator. The entire efficiency advantage depends on recovering more than 90% of the exhaust heat. That requires printed circuit heat exchangers, thousands of chemically etched microchannels fused into a solid metal block. They're extraordinarily efficient, but essentially impossible to inspect internally. And at 200 atmospheres, a micro crack isn't a maintenance issue, it's a catastrophic failure. Third, the spinning hardware. At 30,000 RPM, conventional oil-lubricated bearings self-destruct from friction heat. You need magnetic bearings that levitate the shaft with no physical contact, which means constant power consumption, backup systems, and enormous complexity. Or gas foil bearings using the CO2 itself, which means your bearings must function at 200 atmospheres. The fourth challenge that almost nobody talks about is seals. At 200 atmospheres, CO2 molecules are small enough to leak through gaps that would be perfectly adequate for steam systems. Dry gas seals are the current solution, but long-term reliability data at these pressures and speeds simply doesn't exist yet. But this isn't just a China versus America story. South Korea's KAIST and KAERI are developing SCO2 cycles specifically for next-generation nuclear reactors. Japan's Toshiba is working on concentrated solar applications. The European SCO2 HERO project is exploring nuclear safety systems. India's IGCAR is researching integration with fast breeder reactors. And then there's Net Power. Net Power, based in Texas, runs a different flavor of this technology called the alum cycle. Instead of a closed loop, it actually burns natural gas in pure oxygen, uses the combustion-generated CO2 as the working fluid, and captures all the carbon dioxide as a byproduct. Their 50-megawatt thermal demonstrator has already run in La Porte, Texas, and they've announced a 300-megawatt commercial plant. Claimed efficiency, 59%. With built-in carbon capture, no smokestack. If that works at scale, it doesn't just compete with steam turbines. It makes every conventional natural gas plant on Earth obsolete overnight. So, where does this actually go? The honest answer? We're probably 10 to 15 years away from seeing supercritical CO2 turbines deployed at the 100-megawatt plus scale in primary power generation. The materials science needs more time. The long-term reliability data simply doesn't exist yet, and the manufacturing supply chain for printed circuit heat exchangers and nickel superalloy components is nowhere near the scale required for mass deployment. But the trajectory is clear. Every major nuclear vendor designing Generation 4 reactors, sodium-cooled fast reactors, molten salt reactors, lead-cooled systems, is planning their power conversion around SCO2 Brayton cycles. The global market could reach $5 to $15 billion by the late 2030s. And here's the part that should concern American policymakers. China is doing with SCO2 turbines exactly what it did with solar panels and batteries, getting the first commercial unit running, accumulating operational data, driving down manufacturing costs through iteration, and building the supply chain before anyone else. We spent 166 years perfecting steam, the Rankine cycle, the workhorse of civilization, and the irony is that the thing replacing it, the Brayton cycle, was invented only 13 years later in 1872. We've had the theoretical blueprint for 153 years. The question was never whether supercritical CO2 would work. It was whether we could build materials precise enough, seals tight enough, and bearings clever enough to make the engineering match the physics. China just proved that we can. Whether America responds or watches from the sidelines, that's the story of the next decade.